The story of gravity begins with a paradox. Among all the known interactions that govern the universe, gravity is by far the weakest. A small household magnet can lift a paperclip against the entire pull of the planet beneath it. Yet this same fragile force is what binds galaxies together across billions of light years, what shapes the birth of stars, and what dictates the destiny of the cosmos. How can something so feeble on small scales rule so absolutely on the grandest ones? Physicists have wrestled with that question for centuries. Isaac Newton described gravity as a universal attraction acting between all masses. His mathematics explained the dance of the planets and the falling of an apple with astonishing precision. But he did not claim to know what caused it. When asked, he simply said he framed no hypotheses. To Newton, gravity was a given fact of nature, a rule without a reason. Centuries later, Albert Einstein replaced that idea with a far deeper picture. In his general theory of relativity, space and time themselves become the medium through which gravity acts. Matter tells space-time how to curve, and curved space-time tells matter how to move. There is no invisible force reaching out across empty space. Instead, there is geometry, the bending of the cosmic fabric itself. Einstein's equations transformed physics. They predicted the bending of starlight, the expansion of the universe, and the existence of black holes. But they still did not explain why space-time curves in the first place. They showed how gravity behaves, but not what it fundamentally is. The theory gives an elegant description of the symptom, not the origin. To this day, gravity remains the most mysterious of all the natural phenomena. Quantum mechanics, which governs the microscopic world of atoms and particles, describes everything else with remarkable accuracy. The electromagnetic, weak, and strong forces all fit neatly within its framework. But gravity resists this unification. It does not behave like a quantum field, nor does it submit to the ordinary rules of particle exchange. Every attempt to quantize it directly leads to infinities that make no physical sense. This disconnect between gravity and the quantum world is the deepest rift in modern physics. It is as though nature speaks two incompatible languages, one for the large, one for the small. Yet the universe is one system. Somewhere, these languages must translate into each other. Somewhere, the geometry of Einstein must meet the probabilities of quantum theory. Part of the problem lies in the scale of gravity's weakness. The gravitational coupling is roughly 40 orders of magnitude smaller than that of electromagnetism. Only when masses reach astronomical proportions does it become noticeable. The human brain, tuned to forces we can feel and see, struggles to grasp how such a delicate influence could dominate the architecture of galaxies. Another clue comes from the fact that gravity has no opposite. Electric charge can cancel out, magnetic poles can oppose, nuclear forces balance and saturate. But mass and energy only attract. The universe does not appear to allow negative mass to neutralize positive mass. That one-sidedness is unlike any other field known to physics. It suggests that gravity is not a field in the usual sense. Perhaps it is not a force at all, but a manifestation of something deeper. When we look closely, even the concept of space-time itself starts to tremble. Quantum mechanics teaches that nothing can be perfectly smooth or continuous. The vacuum seethes with fluctuations. Virtual particles appear and vanish in unimaginably small timescales. If space-time is a fabric, then it cannot be infinitely fine. It must have a weave, a grain, a quantum texture. That means Einstein's continuum, however elegant, is only an approximation, like a map that smooths over the details of a terrain it cannot resolve. What could the true substrate be? Some researchers now suspect that what we call space, time, and even gravity are not fundamental at all. They may be emergent, large-scale consequences of more primitive, microscopic ingredients. In the same way that temperature emerges from the collective motion of molecules, gravity could emerge from the collective behavior of information at the quantum level. If that is true, then the curvature of space-time is not a basic feature of the universe, but an illusion that arises from deeper patterns of quantum entanglement. Entanglement is the invisible linkage that allows distant particles to share a single quantum state. It is not a signal or a force, but a correlation, a kind of hidden order in the probabilities themselves. Increasing evidence suggests that these connections could be the scaffolding from which geometry and gravity both arise. The idea sounds radical, yet it has begun to gain traction among some of the most serious theorists in physics. They are re-examining the very foundation of Einstein's picture, asking whether gravity might be nothing more than the thermodynamic result of information-seeking balance. In that view, the universe evolves the way heat flows, not because of forces, but because of the statistical behavior of its underlying information. If the entire cosmos is an information system, then energy, matter, and spacetime would all be emergent properties of quantum bits, the smallest units of information possible. The flow of these bits, their correlations and entropy, might be what we interpret as gravity. The apple falls, the planets orbit, and light bends not because masses pull on each other, but because the geometry of information favors those paths. This would explain why gravity always attracts, entropy always increases, and systems always move toward configurations of greater informational balance. What we feel as the weight of our bodies pressing against the ground might be the local expression of the universe's continual drive toward equilibrium. The downward pull is not a tug from below, but a push from the statistics of the whole. The notion that gravity could emerge from quantum information marks a profound shift in how we think about reality. It suggests that space is not a stage upon which physics happens, but a product of the play itself. It suggests that the structure of the universe is woven not from matter or energy, but from correlations, from meaning encoded in the relationships among quantum states. This perspective does not diminish Einstein's theory. It deepens it. His equations may describe the shadow cast by a more fundamental informational process, just as the laws of thermodynamics describe the collective result of molecular motion. In this sense, Einstein's space-time curvature could be the macroscopic imprint of microscopic entanglement. As we follow this trail, the question shifts from what causes gravity to what causes geometry. Why does the universe have the shape it does? Why do distances and durations exist at all? The answers may not lie in the realm of fields and forces, but in the logic of quantum information. To uncover that logic, we must first revisit the geometry Einstein described, to see how space and time, once thought absolute, became dynamic and curved. Only then can we begin to ask what might lie beneath that curvature, waiting to emerge from the quantum depths. The story of how gravity transformed from a mysterious pull into a dynamic fabric begins with a simple realization. Motion feels different depending on where you stand. When you ride in an elevator and it suddenly rises, you feel pressed to the floor. When it falls, you feel lighter. To Einstein, this similarity between acceleration and gravity was not a coincidence. It was a clue. He called it the equivalence principle, the idea that gravity and acceleration are locally indistinguishable. From that seed grew the general theory of relativity, a framework that reimagined the universe not as a stage of separate space and time, but as a single, four-dimensional continuum that bends and flexes. In this new picture, matter does not pull on matter across empty space. Instead, mass and energy distort space-time itself, and everything, from photons to planets, simply follows the straightest possible paths within that curved geometry. It is a breathtakingly elegant vision, yet elegance can sometimes disguise incompleteness. The equations of general relativity work perfectly until you push them to extremes. Inside black holes, the curvature becomes infinite. At the beginning of the universe, the same equations predict a singularity where density and temperature exceed any physical limit. In those places, the mathematics collapses, and Einstein's picture loses its meaning. Physicists quickly learned that this failure is not an accident, but a signpost. Singularities are telling us that the smooth fabric of spacetime cannot be fundamental. When distances shrink to the Planck length, roughly 1/10 million trillion trillionth of a meter, the very notion of a continuous geometry breaks down. The curvature is no longer a gentle warping, but a chaotic quantum froth. If we want to understand gravity at that level, we must look beyond Einstein's map and ask what the terrain beneath it truly is. For decades, theorists have pursued that question through many paths. Some tried to quantize gravity directly, treating spacetime as another field that can be chopped into particles called gravitons. Others proposed that tiny vibrating strings form the basic ingredients of reality, with gravity emerging from specific modes of vibration. These approaches have produced powerful mathematical tools and deep insights, yet none has fully bridged the gap between the smooth continuum we observe and the quantum chaos we suspect lies beneath. Meanwhile, experiments have confirmed Einstein's theory with ever-increasing precision. Light bends around massive objects exactly as predicted. The orbit of Mercury precesses at the rate his equations demand. Gravitational waves ripple through the cosmos, stretching and squeezing space itself as giant black holes collide. But even as these triumphs unfold, the mystery only deepens. If the theory works so well, why can we not reconcile it with the rest of physics? One reason is that gravity is intrinsically geometric, while quantum mechanics is intrinsically probabilistic. Geometry deals with definite distances and curvatures. Quantum theory deals with uncertainties and superpositions. Trying to merge the two is like painting with oil and water. When we compute quantum corrections to Einstein's equations, the results explode into infinities that defy interpretation. It is as if nature refuses to let space-time be both curved and quantum in the same simple sense. Yet hints of a deeper unity keep appearing. Black hole thermodynamics revealed that a black hole has a temperature and an entropy proportional to the area of its event horizon, not its volume. That simple fact implies that the information describing everything inside is somehow encoded on its surface. The universe, it seems, keeps whispering that information and geometry are entwined. If entropy measures information, then perhaps gravity itself is a statistical effect of that information. When mass gathers, the distribution of information changes and spacetime responds. The curvature we interpret as a force may be the visible trace of invisible bookkeeping, the universe adjusting its informational balance. In that sense, gravity would not be a fundamental field, but an emergent phenomenon, much like pressure or temperature. Those quantities do not exist for individual molecules. They emerge from collective behavior. Perhaps space-time and gravity emerge the same way from the collective behavior of quantum information. Consider how water behaves. At a molecular level, it is a swarm of vibrating hydrogen and oxygen atoms. Yet when billions upon billions of them interact, something new appears. Waves, currents, and the pressure that pushes against your hand. These macroscopic properties arise only when you look at the whole. Einstein's spacetime might be the cosmic equivalent of such a fluid, a large-scale manifestation of something more microscopic and discrete. The notion becomes even more intriguing when you recall that gravity interacts with everything that carries energy. Light, matter, and even the vacuum itself all contribute to curvature. But what if this responsiveness is not a sign of universality, but a clue that gravity is information, trying to find equilibrium across all energy forms? In this reading, Einstein's equation, energy determines curvature, is simply the statement that information content determines geometry. Physicists are now exploring this possibility with fresh tools drawn from quantum information theory. They are asking whether spacetime could emerge from the network of entanglements among quantum bits, the fundamental yes-no units that underlie all physical states. If those bits connect in certain patterns, the resulting web could behave like a curved manifold, with gravity arising naturally from the way information flows through it. This idea does not yet yield a complete theory, but it reframes the question. We no longer ask what gravity is made of, but what kind of computation the universe performs to make it appear. It also shifts how we think about emptiness. What we call vacuum is not nothingness, but a rich sea of quantum potential, alive with fluctuations. The geometry of that sea may depend on how information is distributed within it. If the distribution changes, the curvature changes, and gravity changes with it. In that sense, the emptiness between stars is not void, but structure, the silent architecture of information itself. As this view unfolds, a new narrative begins to take shape. The cosmos might be a self-organizing information system where space, time, and matter are emergent variables. The weakest force, gravity, would then be the most fundamental in appearance, but the most derivative in origin. A surface phenomenon arising from a deeper informational substrate. That is the paradox that defines the modern search for the origin of gravity. Einstein's insight transformed the way we see the universe, but it may not be the final word. His curved spacetime could be the visible skin of a hidden computation, a grand entanglement network whose nodes and links give rise to geometry. To follow that idea, we must descend beneath the mathematical surface of relativity and explore the realm where quantum information reigns, where bits, not atoms, may form the true building blocks of reality. To glimpse the depth of this mystery, imagine standing in the stillness of night, gazing up at the band of the Milky Way. Every point of light you see, every star, every cluster, every shadowed cloud, is held together by gravity. Yet none of these structures should exist if gravity were only a mechanical pull between particles. The stars within a galaxy move too fast to remain bound under Newton's description alone, and the observed mass of visible matter cannot account for the binding we see. Something unseen maintains the coherence of these vast systems. The traditional explanation is dark matter, a hidden substance that provides additional gravitational attraction. But another interpretation is emerging, that the very behavior of gravity on cosmic scales might not be fundamental at all, but a large-scale reflection of deeper informational laws. This notion invites us to think differently about what space itself means. Einstein taught that space-time is a dynamic entity, not a rigid background. But if the geometry of space is dynamic, then its origin must also be dynamic. It must arise from relationships that change, evolve, and balance one another. Those relationships may be informational, not material. When we say space-time curves, we may be describing how the web of quantum information reconfigures itself in response to energy, entropy, and correlations. In this light, gravity becomes the macroscopic whisper of microscopic entanglement, a conversation happening beneath what we call reality. Such a picture resolves certain paradoxes that have haunted physics for decades. The problem of black hole information loss, for example, stems from the classical view that anything falling into a black hole disappears forever. Yet quantum mechanics forbids information from being destroyed. If space-time itself arises from information, then the apparent loss is an illusion. The information may simply be redistributed across the horizon or encoded holographically on its surface. The geometry we see as a black hole would then be the visible expression of how that encoding occurs. This shift also clarifies why gravity interacts universally. In the emergent view, every form of energy contributes to the informational state of space-time. Since information encompasses all possible quantum states, gravity appears to couple with everything. It is not that gravity acts on matter, but that matter and geometry are two sides of the same informational coin. When energy changes, information changes, and space-time adjusts accordingly. The result is what we measure as curvature, acceleration, and weight. The question that lingers is whether this informational perspective can ever be tested. For a theory to move from philosophy to physics, it must make predictions that can be verified. Some researchers believe subtle deviations from Einstein's equations may appear in regions of extremely weak gravity, such as the outer reaches of galaxies. Others propose that quantum correlations between massive objects might reveal the informational underpinnings of spacetime in laboratory experiments. These efforts are still in their infancy, but they share a unifying vision. That gravity, far from being an external force, may be the geometry of information striving for balance. In that vision, the story of the universe becomes the story of information organizing itself. The Big Bang would then mark not the birth of matter, but the birth of computation. The moment when raw potential began to structure itself through relationships. Space would expand as the network of connections grew. Time would emerge as the order of informational updates. Energy would represent the capacity for transformation within that network. And gravity, always attractive, would express the universal tendency for information to distribute itself as evenly as possible across the cosmic web. It is a vision that unites the abstract and the tangible, turning physics into a form of meaning. To say that gravity emerges from quantum information is to suggest that the universe is not merely made of stuff, but of structure, correlation, and memory. It hints that reality is less like a machine and more like a vast story being continuously written, where each bit of information influences the shape of the whole. The galaxies that spiral through the dark, the planets that orbit suns, the atoms that hold us together, all may be chapters in that ongoing computation. Einstein once wrote that the most incomprehensible thing about the universe is that it is comprehensible. Perhaps what he sensed was the hidden order of information that makes comprehension possible at all. If space-time and gravity are emergent, then consciousness too may be an emergent property of the same informational fabric, a localized awareness of the greater network to which it belongs. Our ability to question gravity's origin might itself be a reflection of the universe contemplating its own structure. Still, humility demands caution. No one has yet derived a complete theory that unites general relativity with quantum information in a way that produces testable equations. The mathematics is formidable, the conceptual challenge is profound, but the growing hints, from black hole thermodynamics, from holographic dualities, from the deep connections between entropy and geometry, suggest that we are approaching a turning point. If gravity is indeed emergent, then Einstein's legacy will not be undone, but elevated. His curved space-time will be seen as the grand visible shadow of an even deeper simplicity, the logic of quantum information unfolding across the cosmos. The force that binds galaxies and shapes the fate of stars would then be not a fundamental tug, but the echo of a universal computation, forever seeking equilibrium. The question that began this journey, what causes gravity, may not have a single answer, because gravity might not be a cause at all. It may be a consequence, the visible trace of the universe's invisible conversation with itself. In the stillness between stars, in the curvature of light around a distant cluster, in the weight we feel beneath our feet, the universe may be whispering the same message, that everything, from the smallest quantum to the largest galaxy, is bound together by the flow of information. And so the paradox with which we began comes full circle. Gravity, the weakest of forces, may owe its power not to strength, but to universality, to the fact that information touches everything. From this perspective, the cosmos is not ruled by a force that pulls, but by a principle that unites. What we call gravity may be nothing less than the geometry of meaning itself. Gravity was once imagined as an invisible hand stretching through emptiness, an unseen thread binding all things with silent authority. Newton's law of universal gravitation gave that thread form. It declared that every mass in the universe attracts every other, and with that simple idea, he explained both the falling of an apple and the orbits of planets. His mathematics worked so perfectly that it ruled science for more than 2 centuries. Yet Newton himself admitted that he did not know what caused the attraction. He could describe how gravity behaved, but not why it existed. The mystery deepened as instruments grew more precise. Astronomers noticed that Mercury's orbit drifted slightly from Newton's predictions. Light, though it had no mass, seemed to bend near the Sun. These were small hints that gravity was more than a mere pull between objects. It was something woven into the fabric of existence itself. Einstein recognized this not as a failure of Newton's insight, but as an invitation to reimagine the problem entirely. He began with thought experiments simple enough to picture in the mind. Imagine falling freely through space. You would feel weightless, as though gravity had vanished. Now imagine standing in an accelerating elevator in deep space. Your feet would press against the floor, just as if you were in a gravitational field. Einstein saw that these two experiences were indistinguishable. The feeling of gravity and the sensation of acceleration were the same phenomenon viewed from different perspectives. From that seed grew a revolution. The principle that gravity and acceleration are equivalent revealed that gravity is not a force in the traditional sense. It is the shape of spacetime itself. Mass and energy do not pull on distant bodies. They bend the geometry of the universe, and everything within it moves along the straightest possible paths through that curved geometry. The planets orbit the Sun not because they are being pulled, but because the Sun's mass has curved spacetime in such a way that their natural motion traces a circle through it. Einstein's equations turned the cosmos into a living geometry, dynamic and self-consistent. Space and time were no longer separate entities, but aspects of a single, four-dimensional continuum that could stretch, ripple, and fold. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. The elegance of this relationship reshaped physics, uniting motion, energy, and geometry into one seamless description of reality. Yet the deeper beauty of Einstein's theory lies in how it abolishes the concept of empty space. What we call space is not nothingness, but an active participant in the drama of the universe. Even in the apparent void, geometry exists, energy flows, and time itself stretches and contracts. Gravity, once thought to be a simple attraction between masses, is now understood as the manifestation of that dynamic fabric. Every star, every planet, every person leaves a subtle imprint on spacetime, altering its curvature and in turn being guided by it. But this elegant picture comes at a price. Einstein's mathematics predicts its own limits, points where the curvature of spacetime becomes infinite and the equations lose meaning. At the heart of every black hole, where matter collapses under its own weight, the theory breaks down. The same happens if we wind the cosmic clock backward to the birth of the universe. The Big Bang appears as a singularity, a boundary beyond which Einstein's fabric cannot be stretched. These singularities suggest that spacetime, no matter how smooth it seems, cannot be fundamental. Something deeper must underlie it, something that remains meaningful where geometry fails. Then, there is the other great framework of modern physics, quantum mechanics. It describes a world where certainty dissolves into probability, where energy and position fluctuate, and where every particle exists as a wave of possibilities. General relativity, by contrast, paints a serene and continuous picture of spacetime, perfectly smooth and predictable. These two visions of nature refuse to coexist peacefully. When physicists try to combine them, infinities appear again, and the mathematics collapses. The smooth fabric of spacetime cannot survive at the scales where quantum uncertainty dominates. This clash is not merely technical, but philosophical. It challenges the assumption that spacetime itself is the stage upon which physics unfolds. If the fabric of the universe frays at the smallest scales, perhaps it is not the foundation, but the outcome. A large-scale pattern emerging from something more primitive and discrete. Just as temperature arises from the collective motion of molecules, space-time might arise from the collective organization of microscopic information. And so the mystery deepens. Einstein showed us that gravity is geometry, but he did not tell us what geometry is made of. What is the substance of spacetime? What are its atoms, its smallest indivisible elements? If geometry is emergent, then the true essence of gravity might not be mass or curvature, but information, the way quantum states connect, correlate, and evolve. Beneath Einstein's smooth equations could lie a vast web of invisible relationships, a network of entanglement from which space, time, and gravity all arise together. The search for that hidden architecture of reality begins here, in the curved geometry Einstein revealed, a universe where motion follows the shape of space itself, and where the very fabric of existence might be nothing more than the shadow of something deeper, waiting to be uncovered. Einstein's picture of gravity as geometry was both triumph and tease. It unified celestial mechanics and the falling of an apple under a single principle. Yet it opened a chasm of questions about the true nature of the fabric he described. If space-time can stretch and curve, can it also have texture? Can it fluctuate? The equations imply that it can. Gravitational waves ripple through it when masses accelerate, like tremors spreading across a cosmic sea. But what is it that ripples? What is the medium of this invisible ocean? When we look closely, the analogy becomes haunting. A ripple in water is not a thing apart from the water itself. It is the motion of the medium. In the same way, a gravitational wave is not something traveling through space. It is space itself undulating. Einstein's mathematics captures this perfectly, yet it stops short of telling us what space-time is made of. If it can move and vibrate, it must have a form of structure, a pattern capable of storing and transmitting information. But no experiment has yet revealed any smallest unit of that pattern. On the scale of planets and galaxies, relativity reigns supreme. The orbits of worlds, the bending of light, and the slow dance of time near massive bodies all follow its predictions with exquisite accuracy. Yet on the scale of atoms, the theory falls silent. Quantum mechanics rules there, and in that realm, nothing is smooth or continuous. Fields fluctuate, energy exists in discrete quanta, and probability replaces certainty. If the universe is quantum at its heart, then space-time itself should not escape that rule. It too should be quantized, composed of elemental bits of information that build the geometry we perceive. But our intuition rebels. We experience space as continuous and time as flowing. The challenge of unifying relativity and quantum mechanics lies partly in this illusion. Our senses, evolved to navigate middle scales, are blind to the discrete structure that may underlie reality. Physicists have long suspected that at distances near the Planck length, roughly 1/10 million trillion trillionth of a meter, the smoothness of space dissolves into a foamy chaos of quantum fluctuations. Space-time at that scale might flicker, expanding and contracting wildly, creating momentary tunnels and bubbles of curvature that appear and vanish before they can be measured. If this image is true, then Einstein's continuum is not wrong, but incomplete. A magnificent approximation, like the surface of the ocean seen from afar. Only up close do we notice the froth and turbulence that define its true nature. The same may hold for gravity. The gentle curvature we observe on astronomical scales could emerge from the ceaseless quantum storm beneath. Hints of that storm appear when we study black holes. These objects are the purest expression of Einstein's geometry, regions where curvature becomes so intense that nothing, not even light, can escape. Yet, when quantum mechanics is applied to their boundaries, strange things happen. Black holes are not perfectly black. They radiate energy, and that radiation carries temperature and entropy. The discovery by Stephen Hawking that black holes emit heat was a revelation. It implied that gravity, geometry, and thermodynamics are entangled at the most fundamental level. Entropy is a measure of information, of how many microscopic configurations a system can have. If a black hole possesses entropy, then its surface encodes information. The area of the event horizon, not the volume inside, determines how much information it can store. This fact suggests that the contents of a region of space are somehow represented by data on its boundary. Reality, it seems, may be holographic. The three-dimensional world we inhabit could be a projection of information inscribed on a two-dimensional surface. Einstein's theory did not predict this, yet it seems to grow naturally from it. The equations of general relativity remain valid, but their meaning shifts. Curvature becomes the way information arranges itself, the shape taken by correlations among quantum states. The universe, in this view, is not made of matter moving through space. It is made of information forming space. The transition from Newton's force to Einstein's fabric was one of the greatest intellectual leaps in human history. But now, another transformation looms, one that may prove even deeper. If gravity arises from information, then spacetime is not the ultimate reality, but an emergent construct, like temperature or pressure. Those familiar properties do not belong to individual molecules, but to the collective behavior of many. Likewise, gravity may not belong to any particle or field, but to the collective organization of quantum information across the universe. This perspective could explain why gravity is so weak compared to the other forces. The electromagnetic, weak and strong interactions are direct manifestations of quantum fields. Gravity, by contrast, would be a statistical effect, an emergent byproduct of many quantum interactions working together. Just as the warmth you feel on your skin is not a single molecule's energy, but the sum of countless collisions, gravity may be the cumulative tendency of quantum information to find balance. Seen this way, Einstein's geometry is the large-scale reflection of microscopic order, the calm surface of an informational ocean. The bending of light around a star, the orbit of a planet, and the fall of an apple would all be macroscopic echoes of patterns billions of times smaller than atoms. The shape of the universe would be the expression of how information flows within it. As this idea takes hold, the boundary between physics and information theory begins to blur. The laws of nature may not describe matter and energy alone, but the logic by which information is processed and exchanged. Gravity, the oldest mystery of motion, could then be the visible sign of that invisible computation. It would not be a pull, but a pattern, a silent geometry formed by the ceaseless dialogue of quantum states beneath all things. And if that is true, then the next step in our understanding of gravity will not come from discovering a new particle or a hidden dimension, but from decoding the informational language that writes the universe itself. Einstein once described his discovery of general relativity as the moment he realized that gravity was nothing more than geometry. Yet even he sensed that the geometry might not be the end of the story. In his later years, he sought a deeper unity, searching for the hidden laws that would tie gravity to electromagnetism and the quantum world. He never found them, but his intuition that something more fundamental lay beneath spacetime has only grown stronger with time. To understand why, imagine stripping the universe of all matter, all light, and all fields. What remains is not absolute nothingness, but space-time itself, an invisible framework with its own properties. Even in a perfect vacuum, Einstein's equations tell us that space can curve, expand, or contract. But if geometry can act, it must contain information about its curvature, its rate of expansion, its potential for motion. This realization bridges the abstract world of mathematics with the tangible world of physics. Geometry carries information, and information carries energy. The boundary between them begins to dissolve. Everywhere we look, the fingerprints of this relationship appear. A gravitational wave passing through Earth slightly stretches and squeezes space, altering distances by less than the width of a proton, yet carrying enough energy to have come from colliding black holes billions of light years away. That energy is not an object moving through space. It is a change in the informational structure of space-time itself. Energy, geometry, and information seem to be three expressions of a single underlying reality. The black hole again serves as our most revealing teacher. When matter collapses into one, information about its original state appears to vanish. The object becomes featureless, defined only by its mass, spin, and charge. But if information is truly lost, quantum mechanics collapses because the fundamental laws of physics demand reversibility. The paradox forced physicists to reconsider what a black hole actually is. Perhaps the information is not destroyed, but encoded on the event horizon, spread thinly over its surface in microscopic bits. That idea, first suggested by Jacob Bekenstein and confirmed by Hawking's calculations, gave birth to a profound principle. The entropy of a black hole, and therefore the amount of information it contains, is proportional to its surface area, not its volume. This fact is startling because it implies that the three-dimensional contents of a region of space can be described entirely by information stored on a two-dimensional boundary. The same reasoning might apply not just to black holes, but to the universe itself. What we perceive as three-dimensional reality could be a projection of quantum information encoded on a cosmic horizon. The gravitational field, in that case, would not be a force acting in space, but the curvature of the information encoded on that horizon. In this new light, the concept of distance itself becomes relational. 2 points are close, not because of coordinates on a grid, but because the quantum information that defines them is strongly correlated. When those correlations weaken, distance increases. Space, then, is nothing more than the pattern of connections between bits of information. Gravity arises when those connections evolve in such a way that the structure bends. Geometry becomes the language through which information expresses itself. This idea, once purely speculative, has gained support from the strange symmetry known as the holographic correspondence, or more precisely, the anti-de Sitter conformal field theory relationship, often written as ADS-CFT. It shows that a universe with gravity in higher dimensions can be equivalent to a quantum field theory without gravity on its lower dimensional boundary. In that equivalence, geometry and information are two sides of one coin. The curvature of the higher dimensional spacetime corresponds directly to the pattern of entanglement in the lower dimensional system. Gravity, in other words, can emerge from quantum information. The deeper implication is that the universe may not contain information. It is information. What we call matter and energy are manifestations of how that information is organized. When the organization changes, the geometry changes, and that change manifests as gravity. The curvature of space-time becomes the visible consequence of information-seeking equilibrium. This view also reshapes our understanding of causality. In a purely geometric universe, cause and effect are encoded in the structure of space-time. But in an informational universe, causality itself may arise from the order in which information is processed. The flow of time could be nothing more than the direction in which information spreads and entanglement increases. The arrow of time and the pull of gravity might both emerge from the same statistical principle. The universe evolving toward higher entropy, toward a more balanced distribution of information. As radical as this sounds, it restores a kind of unity to physics that has been missing since the early 20th century. Gravity, thermodynamics, and quantum mechanics are not separate chapters, but variations of one theme: information. Energy is the capacity to change information. Entropy measures the amount of information hidden from view. Geometry is the map drawn by those changes. Gravity then becomes the music of that hidden dance, the visible rhythm of information flowing through the universe. What began with Newton's invisible hand and Einstein's curved space-time may end in something even more profound: the recognition that space and time themselves are illusions born of information. The universe, vast and luminous, may not be a collection of things, but a single computation unfolding in real time, writing and rewriting its own geometry as it goes. If this is true, then the story of gravity is the story of meaning itself, of how the raw data of the quantum world becomes the structured reality we inhabit. And though Einstein could not have known it, his equations may have been the first glimpse of that hidden code, the geometry through which the universe tells the tale of its own existence. Quantum information is the most elemental currency of existence. Beneath the waves of matter, beneath the fields and particles that populate the cosmos lies something far more abstract, the logic that governs how possibilities become real. It is the grammar of reality, the code through which the universe computes itself. While classical information can be reduced to bits that are either 0 or 1, quantum information transcends that binary constraint. It is stored in qubits, units that can be both 0 and 1 at the same time, a superposition of possibilities that only collapses when observed. This is not merely a clever trick of mathematics. It is how nature behaves. Every electron, every photon, every atom in the universe exists in a state of probability until it interacts with something else. Observation, measurement, and interaction are not passive acts. They are processes of information exchange. The world we perceive as definite and solid is, at its foundation, a tapestry woven from uncertain threads of quantum information. In the middle of the 20th century, physicists learned that information and physical law are inseparable. Landauer's principle revealed that even erasing a single bit of information has an energetic cost. Information is not an abstract bookkeeping device. It is physical. It requires energy to store, to transmit, and to destroy. When information changes, so does the state of the universe. This discovery transformed our understanding of thermodynamics and set the stage for a deeper union between physics and computation. From this perspective, the universe is not merely governed by laws, it performs them. Every interaction between particles can be viewed as a computation in which quantum information is processed, conserved, and transformed. Entanglement is the most mysterious and fundamental of these operations. When two quantum systems become entangled, their properties cease to be independent. Measure one, and you instantly know something about the other, no matter how far apart they are. It is not that information travels faster than light, but that the two systems share a single quantum state spread across space. Einstein called it spooky action at a distance, yet experiments have confirmed it beyond doubt. The violation of Bell's inequalities proved that no hidden local variables can explain these correlations. The universe does not obey the separations that our intuition demands. At the most fundamental level, it is not made of independent objects, but of relationships, patterns of information that span space and time. Entanglement is the glue that binds the quantum world together, the invisible thread from which all structure is woven. If information is the foundation, then energy, matter, and even geometry are emergent expressions of its flow. The equations of quantum field theory already hint at this. Particles are excitations of underlying fields, ripples in invisible seas of probability. Those fields, in turn, can be understood as patterns of information. When a particle interacts, information is exchanged. When two systems become correlated, a new informational structure emerges. Reality evolves not through forces pushing and pulling, but through the continual rearrangement of correlations. Quantum information also challenges our notion of locality. In classical physics, what happens here cannot immediately affect what happens there. But in quantum theory, entanglement ignores such boundaries. The universe seems to operate as a single, interconnected whole, where distance is not a barrier but a parameter, describing how strongly systems share information. This holistic character suggests that spacetime itself might be an emergent consequence of these correlations. Where entanglement is dense, space feels connected. Where it is sparse, space stretches apart. This insight, though radical, is gaining empirical and theoretical weight. In quantum simulations and condensed matter experiments, researchers have observed that the structure of entanglement determines the effective geometry of systems. In certain materials, the way particles are entangled defines the dimensionality of the emergent space within them. It is as though space itself is a byproduct of quantum relationships, a pattern formed by how information is stored and shared. Such a view recasts the universe as a vast quantum network, not a collection of particles moving through a pre-existing void, but a web of informational links that together generate the illusion of space, time, and motion. The equations that describe entanglement entropy mirror those that describe curvature in Einstein's theory. This is not coincidence. It may be the bridge between the quantum and the geometric, the microscopic and the cosmic. Quantum information theory has already revolutionized technology. Quantum computers exploit superposition and entanglement to perform calculations that would take classical machines longer than the age of the universe. In doing so, they mimic nature's own computation. Every atom, every interaction, every fluctuation in the vacuum carries out similar processes effortlessly, continuously. It is as if the cosmos itself is a quantum computer, evolving its own state according to the rules of information. If that is so, then gravity, the smooth curvature that guides galaxies and light, could be the large-scale consequence of this underlying computation. Where information is densely connected, geometry curves inward. Where it is diffuse, space expands. The flow of information would then be the engine that shapes space-time, and the tendency toward equilibrium, the balancing of informational entropy, would manifest as the force we call gravity. This picture also brings a new perspective to the nature of measurement. In quantum mechanics, observation collapses superposition into definite outcomes. In an informational universe, that collapse represents the resolution of uncertainty, the reduction of possible states into a single, realized configuration. Every act of measurement adds to the total information content of the universe. The arrow of time might emerge from this irreversible process, the continual increase of quantum information as the universe computes its own history. To understand quantum information is to realize that everything, space, time, matter, energy, is secondary. The only true constant is the logic of connection, the law that relates one quantum state to another. What we call reality is the visible consequence of that invisible order. In the silence beneath the equations, the universe is continually processing itself, turning uncertainty into form, potential into history. And as we follow this thread deeper, a new possibility emerges, that the geometry of spacetime itself, the smooth continuum Einstein envisioned, is not fundamental, but an approximation of the way entanglement organizes information. The shape of the cosmos could be nothing more than the pattern of its quantum correlations, written large across the void. If this is true, then we have misunderstood the hierarchy of reality. Gravity does not sculpt the quantum world. The quantum world sculpts gravity. The fabric of spacetime may be the grand illusion of countless qubits interweaving, their entanglement forming the very structure of existence. To grasp gravity's origin, we must understand how information itself shapes the universe. For information, not matter, may be the true substance from which all things arise. The realization that information might be the foundation of all things transforms how we see both the smallest and the largest structures in nature. It implies that reality is not built from matter upward, but from information downward. Matter is simply a pattern of stability within a restless sea of possibilities. The electron's mass, the photon's energy, the curvature of spacetime itself, all are expressions of how information arranges itself into coherent forms. In this view, a single quantum bit, a qubit, carries more than just 1 or 0. It holds the entire spectrum of possibility between those extremes. It is like a coin spinning in mid-air, not yet heads or tails, containing both outcomes until it lands. But unlike a coin, the qubit does not truly collapse until it interacts with the universe around it. That act of interaction, of exchanging information, is what we perceive as an event. Reality happens when quantum information becomes shared. This sharing gives rise to entanglement, the most extraordinary property in quantum physics. Two particles that interact become forever linked by a single wave function, even if they drift to opposite ends of the galaxy. The universe does not track them as separate entities. It remembers their relationship. Their fates are correlated because they remain part of the same informational structure. The entangled pair is one system, stretched across space, a living thread in the fabric of existence. When many such threads weave together, an extraordinary thing occurs. A structure resembling space begins to form. Where entanglement is strong, systems feel close. Where it is weak, they feel distant. The topology of these connections defines the geometry of the emergent world. It is no longer that particles exist in space. Rather, space exists because particles are entangled. Distance, curvature, even dimensionality may all be derived from patterns of correlation among quantum bits. This idea is not fantasy. It arises naturally from the mathematics of quantum information. The entropy associated with entanglement, a measure of how much information two regions of a system share, obeys the same laws that describe the curvature of spacetime in Einstein's equations. The more entangled two regions are, the more connected their geometry becomes. In this sense, the equations of general relativity may be nothing more than the thermodynamic limit of quantum information theory, the large-scale shadow of microscopic entanglement. We can see a glimpse of this unity in black hole physics. The entropy of a black hole, as discovered by Jacob Bekenstein and Stephen Hawking, is proportional to the area of its event horizon. That relationship between area and information mirrors the structure of quantum entanglement. It hints that spacetime's geometry, the very notion of area, volume, and curvature, arises from how information is distributed and shared. In other words, geometry is not a stage. It is a story told by information. If this is correct, then every moment of existence is a computation, a processing of information at the quantum level. The universe does not simply evolve, it calculates. The flow of time is the order in which these computations occur. The natural sequence of information updates across the cosmic network. Energy is the capacity for those updates to take place. Entropy is the record of what has already been processed. This picture also transforms our understanding of randomness. In the classical sense, randomness is ignorance, a lack of knowledge about what will happen next. In the quantum sense, it is intrinsic. But if the universe is fundamentally informational, then even quantum uncertainty is a reflection of incomplete correlation. Every probabilistic outcome represents an uncomputed relationship within the whole. As the universe evolves, those relationships are continuously resolved, collapsing possibilities into actuality and expanding new possibilities in return. At this level, there is no clear boundary between physics and computation, or between reality and logic. The same principles that govern the flow of information in a quantum computer may govern the evolution of the cosmos itself. Quantum error correction, the mathematical technique that preserves information despite noise and disturbance, has been found to mirror the structure of spacetime in holographic models. It seems that nature itself performs error correction, ensuring that information is never truly lost, but only redistributed. The consequence of this insight is profound. If information is conserved, then the death of a star, the evaporation of a black hole, even the expansion of the universe must all preserve the total informational content of reality. The universe may change form endlessly, but the total information it contains remains constant. It does not forget. It only transforms. Some physicists have begun to suggest that the entire cosmos can be seen as a quantum code, a self-correcting informational structure that maintains coherence across unimaginable scales. Spacetime, gravity, and matter emerge as the large-scale behavior of this code, much as temperature and pressure emerge from the motion of molecules. What we perceive as smooth curvature may be the average geometry of a vast entanglement network, a web so intricate that its individual strands can never be observed directly. To sense gravity, then, is to feel the shape of information, the pull that anchors us to the Earth, the orbits of planets, the arcs of starlight. All are echoes of the way quantum information seeks equilibrium. The universe bends not because of force, but because of balance. Geometry is the record of how information organizes itself in pursuit of harmony. It is a breathtaking possibility. Every atom, every photon, every grain of dust would be part of an unimaginable tapestry of data, weaving and reweaving itself in time. The past would be the information already written, the future the information yet to be computed. We live inside that computation, experiencing its flow as reality. And if this is so, then the ultimate task of physics is not to find the smallest particle or the largest structure, but to understand the rules of this cosmic code, the logic by which quantum information becomes spacetime, by which correlation becomes curvature, by which meaning becomes matter. For in the end, gravity, space, and time may all be stories written in the same language, a language spoken by the universe itself, one qubit at a time. If spacetime truly arises from the network of entanglement, then our familiar notions of distance, direction, and even dimension are not built in from the start. They are consequences of how information is shared. To imagine such a world, one must abandon the picture of the universe as an empty container filled with objects. Instead, think of reality as a web of relationships, a boundless network where every node is a quantum system and every link represents entanglement. The strength of those links defines what we perceive as closeness, and the overall structure defines the geometry of the cosmos. This picture echoes the logic of quantum error correction, where information is encoded in distributed patterns that can survive local disturbances. In a holographic universe, the same principle may protect the structure of space-time itself. Even if some of the underlying quantum connections are disrupted, the global geometry remains stable, just as a message can be recovered from a redundant code. This self-healing nature could explain why space-time appears so smooth and resilient despite the chaos of quantum fluctuations at its core. Imagine zooming in on the fabric of reality until the continuum breaks apart into discrete nodes of information. Between each node runs a thread of entanglement. Where threads are dense, geometry is tight, and space appears curved. Where they loosen, space expands. A black hole, in this view, is a region where the threads converge so densely that they form a boundary, an informational horizon separating interior from exterior. What we perceive as gravity pulling inward is the tendency of information to condense and equalize across that boundary. In this informational framework, Einstein's field equations emerge naturally as thermodynamic identities. Ted Jacobson in the 1990s showed that if one assumes the fundamental relationship between entropy and area holds locally, the equations of general relativity follow. This discovery suggested that gravity is not a fundamental interaction, but a statistical one, describing the large-scale flow of information toward equilibrium. The geometry of spacetime would then be the macroscopic expression of countless microscopic bits in motion, just as pressure and temperature arise from molecules colliding. Quantum entanglement is the key to this emergence. When two regions of the universe share entanglement, they share geometry. If one were to somehow erase all entanglement between them, the connection would vanish, and the universe would split into separate pieces. Mark van Ramsdonk proposed precisely this, that space-time itself is stitched together by entanglement. In his view, increasing entanglement tightens the fabric, creating continuous space. Reducing it tears the universe apart. Entanglement, not distance, becomes the true measure of separation. This perspective radically redefines what it means for something to exist. To exist in space is simply to be part of the network, to be entangled enough to participate in the common geometry. The vacuum between galaxies is not empty. It is filled with invisible connections, the background hum of quantum information linking everything to everything else. Even the most desolate void carries structure, a whisper of correlation that defines its shape. The holographic principle offers the clearest evidence of this relationship between information and geometry. It arises from the study of black holes, where entropy, the measure of hidden information, scales with the area of the horizon rather than the volume inside. This is the opposite of what one might expect if information were stored in the interior. The implication is staggering. The three-dimensional contents of a region are fully encoded on its two-dimensional boundary. The universe itself might operate by this rule, with the entire cosmos being a projection of information inscribed on a distant horizon. In the anti-de Sitter conformal field theory correspondence, or ADS-CFT, this holographic idea becomes precise. A gravitational universe in higher dimensions is equivalent to a quantum system without gravity on its lower dimensional boundary. The curvature and dynamics of spacetime correspond exactly to the entanglement and energy distribution in the boundary theory. Gravity and geometry are emergent reflections of quantum information, like the shadow of a deeper computation. The fact that such a correspondence works mathematically suggests that the fabric of our own universe may arise the same way. Although our cosmos is not shaped like the anti-de Sitter space used in the model, the correspondence hints at a universal principle. Spacetime and gravity are holographic phenomena. Every patch of the universe may be dual to some quantum information system, with geometry and gravity appearing as large-scale approximations of informational dynamics. When viewed through this lens, even cosmological expansion takes on a new meaning. The stretching of space could reflect the dilution of entanglement, the loosening of informational bonds as the universe evolves. Dark energy, the mysterious pressure driving acceleration, might be the energetic signature of that process, the cost of maintaining geometry as information redistributes itself. This approach also reframes the role of the observer. Observation, in quantum mechanics, is an act of acquiring information. In a universe where geometry depends on information, every act of measurement slightly reshapes the fabric of reality. The observer is not separate from the observed. Both are nodes in the same network, exchanging information and altering the geometry that connects them. Reality is participatory, not static, a computation that updates itself through every interaction. Thus, the progression from Newton's force to Einstein's fabric reaches its next transformation. What began as a pull between masses has become an emergent property of information seeking equilibrium. The universe curves, not because of invisible attraction, but because of the logic of its own structure. The equations of relativity are not the foundation of gravity, but its shadow. The true foundation lies deeper, in the invisible flow of quantum information that gives birth to both matter and space. If we could somehow see the universe at its most fundamental scale, we might not find particles or waves, but patterns, threads of entanglement weaving a self-correcting tapestry. Each pattern would encode relationships that, when viewed collectively, become the geometry of spacetime. And within that geometry, gravity would emerge naturally as the gentle curvature of meaning itself. The path toward understanding gravity's true nature took an unexpected turn at the edge of a black hole. In the 1970s, physicists discovered that these cosmic abysses, long thought to be perfect prisons of light and matter, possess temperature and entropy. That revelation changed everything. It meant black holes are not entirely black. They radiate energy, slowly evaporating over time. This radiation, predicted by Stephen Hawking and built upon Jacob Bekenstein's earlier insight, implied that information and geometry are bound together in ways no one had anticipated. Entropy measures hidden information, the number of microscopic states consistent with a macroscopic description. For ordinary matter, entropy scales with volume. The more space a system occupies, the more microscopic configurations it can contain. But black holes defy that logic. Their entropy scales with the area of their event horizon. Double the surface area, and the information content doubles, even though the volume increases much faster. This simple yet profound fact revealed a deep truth about the universe. The information describing everything inside a region may be encoded on its boundary. It was a revolution of perspective. the birth of what became known as the holographic principle. Just as a hologram stores three-dimensional information on a two-dimensional surface, the universe might store its physical reality on a cosmic screen. The three-dimensional world we experience could be an emergent projection of data inscribed on distant boundaries. Space and gravity, once seen as fundamental, may instead arise from how information is arranged and processed across those surfaces. The holographic principle unites thermodynamics, quantum mechanics, and geometry in a single conceptual framework. It tells us that information, not matter, is the true currency of the cosmos. The gravitational field inside a region is not independent of its boundary. The boundary is the information that determines the interior. What we call curvature, energy, and mass might all be consequences of how much information is stored per unit area and how that information flows. This insight reached its most precise form through a discovery in the late 1990s known as the anti-de Sitter conformal field theory correspondence, often called ADS-CFT. In this correspondence, a universe containing gravity in higher dimensions is exactly equivalent to a quantum field theory without gravity living on its lower dimensional boundary. The physics on the boundary and the physics in the bulk describe the same reality in two different languages. Geometry and gravity emerge from quantum interactions at the edge. To grasp the magnitude of this, imagine a three-dimensional world where every atom, every photon, and every bit of curvature is determined by data written on a two-dimensional surface surrounding it. Every movement within that world, every ripple of gravity, every passage of time, corresponds to a change in the boundary's quantum state. The entire interior is a holographic projection of information encoded at the edge. This is not science fiction, it is a rigorous mathematical result within certain geometries. The correspondence works precisely in spaces with constant negative curvature, anti-de Sitter spaces, though our universe, with its accelerating expansion, does not share that exact shape. Still, the success of the correspondence suggests that holography is a universal principle, a deeper law of nature that transcends any particular geometry. At the heart of this principle lies a startling simplicity. The amount of information that can fit in any region of space is limited not by its volume, but by its surface area measured in Planck units. The tiniest quantum of area conceivable, about 10 to the power of -66 square centimeters. This limit, known as the Bekenstein bound, defines the ultimate density of information. Try to pack more information into a region than its area allows, and it collapses into a black hole. Nature enforces this rule absolutely, as if geometry itself were a guardian of information. This bound hints that spacetime is discrete at its core, composed not of continuous fabric, but of finite informational pixels, Planck-scale quanta of area that encode the relationships between events. Just as digital screens appear smooth from a distance, yet are made of individual pixels, the continuum of spacetime may arise from countless microscopic bits of information. The holographic principle suggests that everything we experience, the motion of stars, the passage of time, even the emptiness between, is the large-scale illusion created by the processing of these bits. In this view, gravity is not a fundamental interaction, but an emergent property of holographic information flow. When matter or energy moves, the information on the boundary must adjust to remain consistent. Those adjustments manifest as changes in geometry, the bending of spacetime. The Einstein field equations, which describe how matter curves space, may thus be the thermodynamic equations of an underlying informational system. The holographic revolution also reshapes our understanding of black holes themselves. What falls into a black hole is not lost as once feared. The information becomes encoded on the event horizon, preserved holographically, even as the black hole radiates away its mass. This solves the so-called information paradox. If information can be stored on the horizon, then the evaporation of a black hole does not destroy it, only transforms its representation. Quantum mechanics remains intact, and the universe remains self-consistent. From this vantage, space-time behaves like a vast quantum computer, continuously updating its code. The boundary encodes, the bulk computes, and the geometry we perceive is the result of that computation. Every bit of curvature, every gravitational wave, every moment of time corresponds to the evolution of quantum information. The cosmos does not contain information, it is information, organized in a holographic architecture. This realization also carries philosophical weight. If reality is holographic, then locality, the idea that things are separated by distance, becomes an approximation. In truth, everything is connected through the boundary, where all information resides. Two distant regions in space might correspond to neighboring bits of data on the holographic screen. The separations we perceive may be illusions born from how our consciousness interprets that information. And yet, even as it demotes gravity from a fundamental force to an emergent effect, the holographic principle elevates our understanding of unity. It tells us that every star, every particle, every thought exists not in isolation, but as part of a single cosmic information field. The same holographic code that writes the fabric of space also writes us. The act of observing, of knowing, is itself a form of holographic participation, a local echo of the universal computation. The next step in this journey is to understand how gravity arises precisely from the statistical behavior of that information. How entropy gradients and informational imbalance can generate what we experience as weight, curvature, and attraction. For that, we turn to a bold and unconventional idea, one that suggests gravity is not only emergent, but entropic, a force born from the universe's endless drive toward equilibrium. The holographic idea changes how we imagine the universe at every scale. It suggests that reality, for all its vastness, might be described by a finite amount of information, that the cosmos itself is a bounded data structure. The interior of every star, the space between galaxies, even the air we breathe may all be projections of information encoded on distant boundaries. Space is not empty, it is meaning made visible. This principle reveals an astonishing consistency across the laws of physics. The equations of thermodynamics, quantum mechanics, and general relativity can all be interpreted as statements about information. Temperature measures the average motion of particles, but it can also be read as the rate at which information is exchanged. Entropy measures disorder, yet it can also describe the number of hidden informational configurations a system can take. Einstein's curvature, which defines gravity, can be rewritten in terms of entropy density and energy flow. The great divide between the quantum and the cosmic begins to dissolve once we translate everything into the language of information. In a holographic universe, the boundaries define the reality within. The cosmic horizon, a spherical surface beyond which light can never reach us, might be the grandest example. It is the ultimate screen, encoding all that occurs within the visible universe. Every galaxy, every field, every burst of radiation may correspond to patterns inscribed on that faraway surface. To understand the universe, one could in principle read the boundary like an ancient text, decoding its fluctuating symbols into the stories of stars and worlds. When one peers into the mathematics, the connection between information and geometry grows even clearer. The entropy associated with a region of spacetime is proportional to its boundary area in Planck units. This simple rule links quantum uncertainty with the smooth curvature of relativity. Each Planck-sized patch of area represents roughly 1 unit of quantum information. Space itself may be built from these indivisible bits, each a pixel of reality. The smoothness we experience is merely the large-scale average of this pixelated structure, just as a photograph appears continuous when viewed from a distance. This discreteness could explain why gravity appears so gentle compared to other forces. The electromagnetic and nuclear interactions arise from direct quantum exchanges, sharp and strong at small scales. Gravity, by contrast, is statistical, the result of averaging over countless informational interactions. Its weakness is the price of its universality. Every form of energy contributes to it because all information participates in the same underlying network. The holographic framework also illuminates one of the greatest paradoxes in physics: the apparent loss of information inside black holes. When matter falls beyond the event horizon, it seems to vanish from the observable universe. Yet quantum theory insists that information can never be destroyed. The holographic principle resolves this conflict by placing the missing information on the horizon itself. The surface becomes a ledger, a perfect record of everything that has fallen in. The black hole's slow evaporation, through Hawking radiation, then releases that information back into the universe in subtle, scrambled form. If the boundary truly encodes the interior, then black holes are not cosmic erasers, but cosmic archivists. They preserve the total informational content of the universe, even as they consume matter and energy. Each black hole is a node in the grand holographic network, converting the complexity of three-dimensional reality into the compact symbolism of a two-dimensional surface. In this way, they reveal the deep unity of physics, that information, not matter, is the fundamental currency of the cosmos. This vision of a holographic reality also reframes the way we think about motion and time. What we call movement through space might simply be the evolution of boundary information, an ongoing rearrangement of encoded patterns. The passage of time could be the sequential updating of this holographic code, each moment a new configuration of the cosmic surface. The flow of causality, the distinction between past and future, may arise from the direction in which information propagates across that boundary. Even consciousness finds a new context here. The mind, like the universe, might emerge from the organization of information, its patterns projected from underlying processes that we cannot yet see. If spacetime is a holographic computation, then awareness may be one of its subroutines, a local reflection of the universal code observing itself. The more we explore the holographic principle, the more it reveals an economy of explanation. Every physical law can be reinterpreted as a statement about how information behaves. The conservation of energy becomes the conservation of informational consistency. The second law of thermodynamics, that entropy never decreases, becomes a statement about information spreading and entangling over time. Even the expansion of the universe could be seen as the natural unfolding of information into new configurations. In the holographic picture, reality is both finite and infinite. Finite because the total information content of the cosmos is bounded by its surface area, infinite because the ways in which that information can interact and evolve are unbounded. Every moment, new correlations are created, new structures form, new meanings arise. The universe does not simply exist. It computes itself, rewriting its code from within. And within that computation lies gravity, the curvature of space-time, the arcs of galaxies, the rhythm of falling bodies. All may be macroscopic expressions of the way holographic information strives for balance. The holographic principle is not merely a mathematical curiosity. It is a revelation of what the universe might truly be. Not matter in motion through emptiness, but information unfolding into form. If the holographic principle is correct, then the deepest truth of the universe may not be found by diving inward to ever smaller scales, but by looking outward, toward its boundaries. The edges of space are not ends, but mirrors, reflecting the entirety of what lies within. Every process, every fluctuation, every quantum event in the interior of the cosmos has its counterpart encoded on the boundary surface. The two are not separate. They are the same reality seen from different perspectives. This notion is as poetic as it is precise. It tells us that we are living in a projection, but not an illusion. The holographic image of the universe is real, bound by the same mathematics that governs thermodynamics and quantum theory. Just as a hologram encodes the full depth of an object in the patterns of light on its surface, so does the cosmos encode its three-dimensional geometry in the quantum information written on its cosmic horizon. If we could somehow read that horizon, we would see everything: the birth of stars, the collapse of galaxies, the fluctuations of vacuum energy, even the imprint of our own existence. But we would not see them as objects moving through space. We would see them as sequences of informational change, bits of data shifting and recombining in an ever-updating pattern. To the boundary, everything that happens is computation. The passage of time is the processing of information. This view also suggests that gravity, long considered the sculptor of space and time, may itself be a byproduct of the holographic code. When information changes unevenly across the boundary, the corresponding geometry inside bends. The curvature of space-time becomes the visible trace of information flow. Matter moves along curved paths, not because of a mysterious force, but because those paths correspond to the most efficient routes through the information landscape. The universe curves to conserve meaning. To many physicists, this realization feels like the completion of a circle. Einstein turned gravity from a force into geometry. The holographic principle turns geometry into information. The hierarchy of reality collapses into a single continuum where matter, energy, space, time, and information are inseparable aspects of one phenomenon. Gravity is the story geometry tells when information organizes itself in balance. Even the cosmic scale obeys this rule. The expansion of the universe can be seen as the evolution of its boundary information. As space grows, new bits are written on the cosmic horizon, preserving the balance between interior and exterior data. The mysterious dark energy driving that expansion may not be a new substance, but a reflection of how the holographic code adjusts to maintain equilibrium. The universe expands because information demands it. Yet the holographic model does more than describe the universe. It changes how we think about reality itself. If all that exists is encoded on a boundary, then the distinction between inside and outside becomes philosophical rather than physical. The world we inhabit is a perspective, a projection within a deeper informational structure that encompasses both observer and observed. What we call locality, distance, and even individuality may be approximations of a more holistic truth. This framework also suggests a kind of cosmic unity. Every region of space, no matter how remote, participates in the same global computation. Every particle, every field, every moment of consciousness is a thread woven into a single tapestry. When we gaze at the stars, we are not looking across an empty void, but into the depths of a holographic pattern that connects us directly to them. The light that reaches us is not merely a signal, it is the unfolding of shared information between distant parts of the same whole. Philosophically, the holographic principle blurs the boundary between physics and metaphysics. It suggests that the fundamental reality of the universe may be abstract, not a collection of things, but a collection of relationships. Reality, at its core, might be meaning itself, quantified and dynamic. The laws of physics would then be the grammar of this universal language, the syntax by which information coheres into existence. We are only beginning to understand the implications. The holographic principle provides a map, but not yet the terrain. It shows that geometry and information are two sides of the same coin, but it does not yet explain how the coin is minted. To uncover that, we must go further, into the domain where information and entropy converge, where gravity may not only emerge from information, but from the very tendency of information to increase. This is where the next great idea enters, that gravity is entropic, born not from force, but from the statistics of information-seeking equilibrium. It is a theory that dares to say the most familiar feature of our world, the pull that binds us to the ground and holds galaxies together, is not a fundamental interaction at all, but a thermodynamic effect of information itself. The holographic revolution set the stage. What comes next is its boldest consequence. The next revolution in our understanding of gravity began not with an experiment or an observation, but with an act of imagination. In the early years of the 21st century, the Dutch physicist Erik Verlinde proposed that gravity might not be a fundamental interaction at all. Instead, it could be an emergent statistical effect, the macroscopic echo of microscopic information striving for balance. In his view, what we call gravitational attraction is not a force pulling masses together, but a thermodynamic consequence of information seeking equilibrium. Verlinde's idea drew from deep connections between gravity, thermodynamics, and information theory, threads that had been weaving together since Hawking's discovery of black hole radiation. If black holes possess temperature and entropy, and if their entropy measures the amount of information stored on their horizons, then perhaps every region of spacetime follows the same logic. Gravity could arise not from fundamental fields, but from the collective behavior of information, just as temperature arises from the collective motion of molecules. To see how this works, imagine an object approaching a holographic screen, a surface that encodes information about the region it encloses. As the object moves, the distribution of information on the screen changes. The system's entropy shifts, and nature resists that imbalance. The object feels a force driving it toward the region of higher entropy, the direction in which information becomes more evenly distributed. That force is what we perceive as gravity. It is not a fundamental pull, but an entropic push, the statistical tendency of information to spread. Verlinde derived Newton's law of gravitation from this principle, showing that the familiar inverse square relationship could emerge naturally from entropy and information. The gravitational constant, rather than being fundamental, would be a conversion factor linking bits of information to physical energy. Space itself would act as an information storage medium, and mass would represent localized information content. Where information density changes, space curves, and what we call motion in a gravitational field becomes the flow of information toward equilibrium. This interpretation transforms our understanding of mass and inertia. An object resists acceleration not because of an inherent property, but because accelerating it requires reorganizing the information associated with its position in the universe. Motion through space becomes motion through an informational field, and the apparent laws of mechanics emerge from the statistics of that field. The idea was daring and elegant, yet also deeply unsettling. If gravity is emergent, then spacetime itself is secondary, not the foundation of physics, but a consequence of informational relationships. The fundamental entities would not be particles or waves, but bits of information and the rules by which they interact. This framework fits naturally with the holographic principle. The entropy on a surface measures the number of microscopic states corresponding to the geometry inside. When matter moves, the entropy distribution changes and the geometry adjusts to maintain consistency. Gravity, in this view, is the bookkeeping of information flow. The Einstein field equations become thermodynamic identities, describing how information gradients translate into curvature. Verlinde's approach also offers a new perspective on dark matter and dark energy, the invisible components that dominate the universe's mass and energy budget. If gravity arises from information, then deviations from Newtonian gravity on galactic and cosmological scales might not indicate missing matter, but additional information contributions from the quantum structure of space-time itself. Verlinde's entropic gravity predicts precisely such deviations, aligning with certain galactic rotation curves without invoking unseen particles. Whether or not this explanation ultimately holds, its implications are profound. It invites us to reconsider what physics seeks to explain. Instead of asking what force causes attraction, we might ask what informational imbalance causes geometry to change. It suggests that the universe is not governed by forces acting at a distance, but by the statistical tendencies of information spreading through an evolving network. The elegance of Verlinde's theory lies in its unification of three pillars of physics: gravity, thermodynamics, and quantum information, under a single conceptual roof. In his picture, entropy, energy, and geometry are not separate phenomena, but different expressions of the same underlying process. The flow of heat, the curvature of space-time, and the distribution of information are all aspects of one dynamic equilibrium. But such an idea demands more than beauty. It demands evidence. Physicists began testing entropic gravity against astronomical data, examining whether it could reproduce galactic rotation curves, lensing effects, and the large-scale structure of the cosmos. The results have been mixed but intriguing. In some cases, Verlinde's framework matches observations remarkably well. In others, traditional dark matter models remain more precise. The jury is still out, but the theory's conceptual power continues to shape the search for a deeper understanding of gravity. If Verlinde is right, then the universe is not a machine of forces, but a self-organizing system of information. Space and time would be emergent properties, like temperature or pressure, arising only when the underlying informational network reaches a certain scale. Below that scale, the very notions of distance and duration would dissolve into the raw flow of data. The cosmos would be a vast computation, its geometry the visible outcome of invisible processing. And if this is so, then gravity is not something added to the universe. It is the universe's way of balancing its own information. The planets orbit not because they are pulled by an unseen hand, but because the informational field of the sun shapes the entropy landscape around it. The apple falls not because it is drawn downward, but because in doing so, the universe increases its informational harmony. The entropic hypothesis reframes one of the oldest forces in nature as a statistical illusion, born from the deepest logic of reality. It points toward a future in which physics may describe not matter and energy, but meaning and computation, the mathematics of how the universe knows itself. In Verlinde's view, the vast web of galaxies scattered across the cosmos is not merely shaped by invisible matter, but by the structure of information itself. The universe, as it expands, constantly redistributes its informational content. Space is not a neutral background stretching outward. It is an evolving informational field, adjusting to balance entropy across unimaginable scales. The curvature we perceive as gravity arises from the collective tendency of that field to equalize its data. At cosmological distances, this framework offers a new way to understand phenomena long attributed to dark matter. When astronomers observe the rotation of galaxies, they find that the outer stars move faster than Newtonian gravity predicts, as though an unseen mass holds them in orbit. Verlinde suggests that no additional matter is needed. Instead, the effect arises from how information in space-time responds to the presence of ordinary matter. The information associated with each particle extends into the surrounding vacuum, and that extended information density contributes to the gravitational effect. In this sense, dark matter is not missing substance, but emergent information. The apparent excess gravity comes from the entropy stored in the structure of space-time itself, an echo of the underlying quantum information that defines the universe. The same logic may explain dark energy, the mysterious pressure causing cosmic acceleration. As the universe expands, the distribution of information changes, generating an entropic force that drives expansion from within. Gravity and cosmic acceleration could then be opposite aspects of the same process. The universe's ongoing effort to balance its informational content. Such a perspective invites us to rethink what expansion means. Traditionally, cosmologists describe the universe stretching, with galaxies moving away from one another through an expanding metric. But if space is emergent, expansion might instead represent an informational unfolding, a a continual creation of new correlations as quantum information spreads. The increase in entropy is not disorder in the usual sense. It is the growth of relational complexity. The cosmos is not thinning out as it grows, but deepening its network of meaning. Verlinde's framework also connects naturally to the holographic principle. Every region of space, no matter how small or large, can be thought of as possessing an associated surface that encodes its informational state. The flow of entropy across that surface corresponds to the curvature of spacetime within. When mass moves, the information on these surfaces adjusts, maintaining equilibrium. The result is what we interpret as gravitational interaction. Geometry, entropy, and energy are not separate realities. They are translations of the same informational process, viewed from different angles. The mathematics of this framework reveals that the entropic force obeys relationships remarkably similar to Einstein's equations, though it arises from entirely different foundations. Gravity, in this sense, is like temperature. It has no meaning at the level of individual quanta, but becomes real when we consider the collective behavior of vast numbers of informational bits. The smooth curvature of spacetime is the statistical average of countless microscopic interactions among quantum states. This statistical nature also explains why gravity resists quantization. Physicists have spent decades searching for a graviton, a hypothetical particle that would carry the gravitational force, but no such particle has ever been detected. In Verlinde's picture, it may not exist because gravity is not a fundamental interaction. Quantizing it would be like quantizing temperature, a category mistake. The true quantum degrees of freedom belong to the underlying informational network, not to gravity itself. At first glance, this might seem to strip gravity of its grandeur, reducing it to a statistical side effect. But the opposite is true. It reveals gravity as the bridge between the microscopic and the cosmic, the visible manifestation of information organizing itself across the largest scales. It ties together black holes, galaxies, and the expansion of the universe into a single, unified narrative. The story of information striving for balance. Verlinde's hypothesis also invites experimental scrutiny. On galactic scales, his equations predict subtle deviations from Newtonian behavior that depend on the distribution of visible matter alone, without invoking dark matter. Observations of some galaxies align with these predictions. The rotation curves flatten where the entropic contribution becomes significant, suggesting that space-time itself carries an informational inertia. However, in other systems, particularly those influenced by galaxy clusters or large-scale interactions, traditional dark matter models remain more accurate. The tension between these results fuels ongoing debate. What cannot be denied is that Verlinde's idea reframes the question entirely. Instead of searching for missing particles, physicists are prompted to ask whether the apparent need for them arises from a misunderstanding of gravity's origin. If space-time and gravity are emergent, then so too is the concept of matter's influence on them. The universe becomes a thermodynamic system, not of molecules, but of information. In that system, entropy is destiny. The direction of time, the curvature of space, the expansion of the cosmos all follow from the universal drive toward maximal information balance. Gravity is the geometry of that drive, the shape taken by the universe's hunger for equilibrium. It is both force and feedback, both effect and expression of the deeper logic that underlies everything. To imagine this is to glimpse a universe that is neither mechanical nor mystical, but informational. A cosmos where every motion is the computation of meaning, every field a flow of entropy, every star a condensation of quantum data. In such a universe, gravity is not an external rule imposed upon matter. It is the story matter tells about the information from which it is made. If gravity is indeed the statistical behavior of information, then Einstein's equations are not the first principles of nature, but the thermodynamic limit of a deeper informational process. What we call space-time curvature would emerge from the collective dynamics of quantum bits exchanging entropy. The universe would not be built upon geometry. Geometry would be the language through which information describes itself. In this view, the Einstein field equations resemble the laws of heat flow. They tell us how curvature responds to energy and momentum, just as thermodynamics tells us how temperature responds to heat and pressure. Ted Jacobson first noticed this connection in the 1990s when he showed that if one assumes the fundamental link between entropy and area, along with the Clausius relation, the law that equates heat flow with entropy change times temperature, Einstein's equations naturally follow. Gravity, then, could be interpreted as the macroscopic expression of information thermodynamics, a statement about how the universe maintains informational balance. Verlinde extended this logic, arguing that the acceleration we experience as gravity is the gradient of entropy. An object moving toward another does so because the entropy of the system increases in that direction. In the same way that gas particles spread out to maximize entropy, masses rearrange their positions in spacetime to equalize information. Motion, in this picture, is the pathway of informational optimization. The geodesics that Einstein described as the straightest paths in curved spacetime become the trajectories of maximal informational efficiency. Seen from this perspective, the universe behaves like a colossal information engine. Every interaction, every exchange of energy, every gravitational movement corresponds to the redistribution of bits. Mass and energy become sources of informational tension, distortions in the balance of entropy that the universe perpetually seeks to smooth out. The result is curvature, the bending of space-time that we interpret as gravity. This analogy extends naturally to black holes. Their horizons represent the ultimate storage surfaces for information, holding the maximum entropy permitted by their area. When matter crosses a horizon, its information becomes encoded on that surface, and the total entropy of the system increases. The black hole grows because information demands space in which to spread. Hawking radiation, the faint thermal glow emitted by black holes, is the means by which that encoded information gradually leaks back into the universe, restoring balance. In Verlinde's framework, this process is not unique to black holes, but universal. Every mass, every field, every patch of space-time participates in the same informational dynamics. The gravitational potential around a star, for instance, is the entropic gradient created by the information stored in its mass. Objects move in response to that gradient, not because they are pulled, but because by doing so, they increase the total entropy of the system. The law of gravitation becomes a statistical consequence of information seeking equilibrium. This principle brings clarity to the mysterious uniformity of the cosmos. The large-scale structure of galaxies, filaments, and voids can be seen as the emergent geometry of an information field expanding and smoothing itself over time. The cosmic microwave background, the afterglow of the Big Bang, may encode the initial conditions of that process, the original configuration of the universe's information field before it began to unfold into the geometry we see today. Even quantum mechanics, long thought to operate separately from gravity, fits naturally into this informational paradigm. Quantum entanglement defines correlations between systems, and the pattern of those correlations determines the structure of spacetime. Where entanglement is dense, geometry becomes connected. Where it weakens, geometry stretches. Gravity thus becomes the macroscopic signature of entanglement flow, the visible curvature caused by information spreading through the quantum web of reality. This convergence of ideas points toward a breathtaking unity. Gravity, thermodynamics, and quantum information may all be faces of the same phenomenon. The equations of motion for matter, the growth of entropy, and the flow of entanglement could be manifestations of a single law: the universe's drive to maximize informational coherence while preserving total information. The cosmos evolves not through external forces, but through internal reorganization of meaning. Such a universe would be self-contained and self-explanatory. There would be no need for a force transmitted through space or a particle mediating gravity. Instead, geometry itself would be a record of information flow. Time would be the sequence of updates to that record. The future would not yet exist because its information has not been computed. The past would persist as the data already written. If Verlinde's vision is correct, then we live within a grand equilibrium engine, a cosmic computation that constantly converts uncertainty into structure. Every star, every orbit, every breath we take participates in that calculation. Gravity is not the hand that holds us, but the equilibrium that includes us. It is the whisper of information balancing itself across the infinite fabric of existence. And as the universe continues to expand and cool, that whisper carries onward, an endless pursuit of equilibrium through the language of geometry, a quiet dialogue between entropy and meaning that defines what we call reality. At the most fundamental level, space-time may not exist as an independent entity at all. It may arise from something far subtler, the invisible bonds of quantum entanglement that link every particle, every field, and every fluctuation of the vacuum. Entanglement is the mysterious phenomenon by which two or more quantum systems share a single state. Measure one, and you instantaneously learn something about the other, no matter how far apart they are. To classical intuition, this seems like magic. To quantum physics, it is the essential thread of reality. Over the past decades, a new picture has emerged. The geometry of space-time itself could be the large-scale expression of how entanglement is distributed. If gravity is information balancing itself, then entanglement is the texture of that balance, the fine-grained web of correlations that defines the shape of the universe. Remove those correlations, and space dissolves. Increase them, and geometry emerges. Mark van Ramsdonk was among the first to see the profound implications of this idea. In the early 21st century, he proposed that the smoothness of space-time arises from quantum entanglement among microscopic degrees of freedom. Imagine taking two regions of space and gradually decreasing the entanglement between them. As the correlations weaken, the geometric bridge that connects them shrinks. When entanglement reaches zero, the regions become entirely disconnected. Space itself tears apart. In this view, the connectivity of space-time, the continuous fabric that Einstein described, is literally built from entanglement. This is more than metaphor. In the holographic correspondence known as ADS-CFT, the amount of entanglement between two regions of the boundary theory is proportional to the area of a surface connecting them in the bulk geometry. Increase the entanglement, and the surface grows. Reduce it, and the surface shrinks. The celebrated Ryu-Takayanagi formula captures this relationship precisely, linking the entropy of entanglement to the geometry of spacetime. Information and area, correlation and curvature are two sides of the same coin. The implications are staggering. If entanglement creates geometry, then the universe is not a stage upon which particles interact. The interactions are the stage. The shape of the cosmos is determined by the quantum relationships among its smallest constituents. Space is a map of information, not an arena that contains it. This idea also suggests that spacetime has a built-in form of redundancy. Just as a quantum computer can protect its information from errors using entangled states, the universe may preserve its own coherence through similar mechanisms. In the ADS-CFT framework, bulk geometry appears to behave like a quantum error-correcting code. Local disturbances, the equivalent of noise in a computation, do not destroy the overall structure because the information that defines space-time is redundantly stored in patterns of entanglement. The universe, in effect, protects its own reality from quantum fluctuations. This redundancy may explain why spacetime appears so smooth and stable, despite the chaotic quantum froth that underlies it. The same principle that safeguards quantum information in laboratory experiments could be operating on cosmic scales, maintaining the integrity of geometry across eons. The universe might be the ultimate self-correcting code, continuously stabilizing its own structure through the flow of entanglement. Entanglement also appears to dictate the dynamics of spacetime, not just its structure. When the pattern of correlations changes, the corresponding geometry must adjust. The flow of entanglement, the way quantum information spreads and redistributes, determines how space evolves over time. In this sense, Einstein's field equations might be the macroscopic equations of entanglement dynamics, describing how the geometry of information changes as energy and matter move. Consider two particles that interact and then separate. Classically, they go their own ways, but quantum mechanically, they remain entangled. Their shared information continues to connect them through an invisible thread. Multiply that by the countless interactions happening every instant across the universe, and you get a web so vast and intricate that it forms the very structure of space. Each quantum interaction adds new links, weaving geometry itself. The flow of time may be nothing more than the continual creation and reconfiguration of these entanglement bonds. This picture provides a natural explanation for why gravity is universal. Every form of energy contributes to entanglement, and entanglement defines geometry. Therefore, all energy affects the curvature of spacetime in exactly the same way. Gravity does not discriminate because it is not a separate force. It is the collective effect of entanglement everywhere. The correspondence between entanglement and geometry also sheds light on one of the deepest puzzles in physics, the nature of wormholes. In the classical theory, wormholes are hypothetical tunnels connecting distant regions of space-time. In the quantum picture, they may correspond to entangled states. The proposal known as ER equals EPR, named after the Einstein-Rosen bridges and the Einstein-Podolsky-Rosen paradox, asserts that every entangled pair is connected by a tiny, non-traversable wormhole. If true, then entanglement is not merely a statistical correlation, but a physical connection, a thread of geometry linking distant points in the quantum fabric. This relationship between wormholes and entanglement unites two of Einstein's most famous ideas into one. The bridges he described in general relativity and the spooky correlations he distrusted in quantum mechanics might be manifestations of the same phenomenon. The universe would then be a vast network of microscopic wormholes, invisible, fleeting, and impossibly small, yet collectively forming the smooth continuum we experience as space. At the same time, this picture brings gravity closer to quantum mechanics than ever before. If space-time is woven from entanglement, then the quantization of gravity is not a matter of finding a new particle, but of understanding how entanglement behaves. The elusive graviton, long sought as the quantum of the gravitational field, may not be a fundamental entity but a convenient approximation, describing the collective oscillations of the entanglement network on large scales. The flow of entanglement also explains the arrow of time. As the universe evolves, quantum information spreads and correlations increase. Entropy grows not because things become disordered, but because more degrees of freedom become entangled. The forward direction of time is the direction in which entanglement expands. The universe remembers its past because the web of correlations continually deepens, encoding history into the structure of geometry itself. This deep connection between entanglement and time challenges the notion of a static spacetime. Einstein's equations describe how geometry bends in response to energy, but in this quantum view, geometry itself is a living process, a dynamic equilibrium of information. Every change in energy distribution corresponds to a change in entanglement, and thus to a change in curvature. The universe is perpetually rewriting its own geometry, computing the next frame of existence through the flow of correlations. The mathematics of tensor networks provides a useful analogy. In these models, complex quantum systems are represented as networks of nodes connected by entanglement links. The geometry of the network resembles a curved space, and the entanglement entropy determines its shape. These networks can reproduce many properties of the ADS-CFT correspondence, suggesting that spacetime might be nothing more than a tensor network realized in nature, an immense, self-optimizing map of correlations. In this sense, the universe is not a static sculpture, but an evolving computation. Space and time are the emergent coordinates of that computation. The smoothness of geometry is the large-scale illusion produced by countless entanglement interactions averaging into continuity. Gravity is the gradient of that computation, the tendency of information to flow along paths of increasing entanglement. When viewed through this lens, Einstein's geometric cosmos and the quantum world of uncertainty finally merge. The curvature of spacetime is the macroscopic shadow of quantum entanglement. The laws of motion are the rules by which information spreads. The universe expands not into emptiness, but into deeper connection, continuously creating new links in its quantum web. And so, gravity becomes not a force pulling on matter, but the whisper of entanglement reshaping geometry. The universe bends because information connects. The fall of an apple, the orbit of a planet, the rotation of a galaxy, all are visible traces of invisible correlations, the grand choreography of quantum information weaving itself into the shape of spacetime. If spacetime is indeed woven from quantum entanglement, then wormholes are not exotic oddities hidden at the fringes of the cosmos. They are the natural filaments of its structure. Every link of entanglement, every quantum correlation that binds particles across distance, could represent a microscopic bridge in the fabric of reality. The universe, seen through this lens, is a boundless network of connections, an immense and ever-changing web in which geometry, gravity, and information are one. The idea that wormholes and entanglement might be two faces of the same phenomenon was crystallized in the proposal known as ER equals EPR. ER stands for Einstein-Rosen, the theoretical bridge connecting two regions of spacetime. EPR stands for Einstein-Podolsky-Rosen, the thought experiment that first illuminated the paradox of quantum entanglement. The conjecture, advanced by Juan Maldacena and Leonard Susskind, suggests that every entangled pair of particles is connected by a tiny Einstein-Rosen bridge. These microscopic wormholes are not traversable in the classical sense, yet their existence reveals a startling truth. Geometry and quantum information are inseparable. To picture this, imagine two black holes that are maximally entangled. According to the ER equals EPR idea, they are connected by a wormhole. Their interiors are joined, though no signal can pass through faster than light. The entanglement between them creates the geometry that links them. The bridge is not an additional structure imposed on space. It is the space that exists between them. Entanglement literally constructs the connection. If this holds at the level of black holes, it may hold everywhere. Every pair of entangled particles could be linked by an unimaginably small wormhole, far too tiny to detect. The smooth continuum of space that Einstein described would then be the collective effect of countless such connections. The universe would resemble a vast quantum network, where each node is a quantum state and each link an entanglement channel. Distance, in this picture, is not a fundamental property, but an emergent measure of how strongly two nodes are connected. Where entanglement is strong, points feel close. Where it is weak, they drift apart. The mathematics of tensor networks captures this idea with remarkable precision. In a tensor network, complex quantum states are represented as webs of interconnected nodes, each node encoding how parts of the system are entangled with one another. When physicists analyze these networks, they find that the geometry they form obeys relationships strikingly similar to those in general relativity. The length of a path through the network corresponds to the amount of entanglement between regions. Curvature arises where the density of connections changes. The entire structure behaves as though it were a piece of spacetime generated from information. This discovery blurs the line between mathematics and ontology. It implies that the universe might not merely be describable as if it were a network. It may actually be one. The web of quantum entanglement is the skeleton of reality, and geometry is the skin stretched across it. Gravity, in this context, becomes the smooth bending of that skin, the macroscopic expression of microscopic connectivity. Quantum error correction further strengthens this picture. In a quantum computer, information is encoded in a way that allows errors from noise or decoherence to be detected and repaired. The ADS-CFT correspondence reveals a similar structure. The boundary theory acts like an error-correcting code for the bulk geometry. Local disturbances in the bulk can be reconstructed from many different sets of boundary data, ensuring that no single region holds the entire truth, but the whole remains consistent. This redundancy is not a flaw, but a feature. It is what allows spacetime to be robust against quantum fluctuations. The universe, it seems, preserves its geometry through the same logic that preserves information in a quantum computer. From this perspective, the distinction between matter and geometry begins to fade. Particles are not entities moving through space, but excitations within the network, localized patterns of entanglement that persist and propagate. Fields are not continuous substances filling space. They are collective behaviors of the underlying informational web. Even the vacuum, the apparent emptiness of space, is filled with entanglement, an infinite lattice of correlations that gives rise to the geometry we inhabit. This framework also provides a natural home for gravity's universality. Since all forms of energy participate in entanglement, all contribute equally to the shape of geometry. There is no need for separate coupling constants or mediating particles. The laws of motion emerge automatically from the informational structure. Einstein's equivalence principle, the assertion that all forms of energy fall alike, becomes a consequence of how entanglement defines connection itself. Wormholes, then, are not speculative tunnels to other universes, but the fundamental bonds of this one. They are the connective tissue of spacetime, the hidden threads that make geometry possible. The cosmic web of galaxies we observe through telescopes may be a faint reflection of a far deeper quantum web, one that underlies all existence. Every particle, every star, every human being is woven into that tapestry, their identities encoded as patterns in a universal network of entanglement. This concept redefines the very notion of location. In a classical universe, two objects are distinct and separated by measurable distance. In a quantum informational universe, distance is a measure of informational disconnection. Two systems that share strong entanglement are close, even if they lie light years apart. The true structure of the cosmos is not defined by coordinates, but by correlations. Geometry is simply the language we use to describe those correlations on large scales. The ER equals EPR idea also provides a possible key to resolving the black hole information paradox. If entanglement generates wormholes, then the information seemingly trapped inside a black hole could be connected to the outside world through quantum correlations. The Hawking radiation escaping from the black hole would not be separate from its interior, but entangled with it through an invisible bridge. Information would not be lost, but encoded non-locally across space-time. The paradox dissolves when we recognize that the universe's geometry is itself a record of information flow. In recent years, physicists have even simulated this idea using quantum computers. By designing small networks of entangled qubits, they have observed behaviors mathematically equivalent to traversable wormholes. Information injected on one side of the network reappears on the other, not because it traveled through space, but because it was transmitted through entanglement. These laboratory models hint that the geometry of spacetime could one day be engineered, that the deep logic of the universe might be recreated in quantum code. If such experiments continue to succeed, they will mark a turning point in the history of science. The ancient boundary between physics and information will vanish completely. Spacetime will be understood not as a static backdrop, but as an emergent network, dynamic and self-organizing, born from the quantum entanglement of its parts. Gravity will stand revealed as the gentle curvature of that network, the large-scale rhythm of information weaving itself into form, In this new picture, the cosmos is a living system of relationships. The galaxies are nodes, the fields are connections, and every event is a reconfiguration of the web. Wormholes are not portals through which we might travel, but patterns that keep the universe coherent. The same entanglement that binds particles across quantum distances binds us to the stars and the stars to the void. Einstein once sought a unified field theory that would merge gravity with quantum mechanics. The solution may have been hidden in plain sight. There is only one field, the field of information. Its excitations appear as particles, its curvature appears as gravity, and its entanglement appears as the very shape of space-time. The universe is not built of matter, but of meaning, and gravity is the geometry of that meaning made visible. If the universe is truly made of quantum information, then gravity is not a force at all. It is a shadow cast by the movement of information through space-time. Every curvature, every orbit, every falling object is the visible trace of an invisible computation, a great balancing act of entropy and meaning. The deeper physicists look into the mathematics, the clearer it becomes. The same equations that describe the spread of quantum information also produce Einstein's field equations. The geometry of the universe may not simply contain information, it may be information. Ted Jacobson was the first to reveal this extraordinary link in the closing years of the 20th century. He showed that Einstein's field equations, the majestic core of general relativity, can be derived from the first law of thermodynamics, provided one accepts that space-time possesses entropy proportional to the area of its local horizons. In simple terms, gravity emerges as a thermodynamic law. Energy flow across a surface changes its entropy, and the resulting geometry obeys Einstein's equations. This is not coincidence, but revelation. The curvature of space-time behaves exactly as if it were the response of an information system striving for equilibrium. Imagine, for a moment, that every region of space-time is a network of quantum bits. When energy passes through that region, those bits rearrange themselves, altering their correlations. The change in entropy determines how much the geometry bends. Gravity, then, is the feedback of information flow. A star curves space-time because the information that defines its mass creates a persistent imbalance, a gradient in entropy. Other objects follow the direction in which this informational tension relaxes, which we perceive as gravitational attraction. Black holes make this relationship unmistakable. Their horizons store information with extraordinary density. 1 bit per Planck area, the smallest measurable patch of space-time. When matter falls into a black hole, its information is not lost, but absorbed into the horizon, increasing its entropy. The black hole's mass, temperature, and curvature are all connected through this information flow. Its gravity is the expression of its informational content. The deeper the well of entropy, the stronger the gravitational pull. The holographic principle expands this connection beyond black holes. It tells us that the entire universe may function as a cosmic information processor. The entropy of a region is encoded on its boundary, and the flow of information through that boundary shapes the geometry within. Einstein's equations describe this flow in macroscopic terms. Quantum information theory describes it in microscopic ones. The two perspectives are not rivals, but reflections of the same underlying process. Physicists have begun to recognize that entanglement itself obeys laws that mirror the laws of gravity. The equations governing the growth and distribution of entanglement entropy bear a striking resemblance to those that dictate the curvature of space-time. When entanglement spreads, geometry expands. When it condenses, geometry contracts. The very dynamics of space-time may be the statistical evolution of entanglement networks. Jacobson's insight becomes a bridge. Thermodynamics translates to geometry, and geometry translates to information flow. In this picture, the universe resembles an ocean of information currents. Mass is a whirlpool, a concentration of informational density. Energy is motion within the current. Gravity is the tendency of the ocean to smooth itself, to restore balance as information spreads. Even inertia, the resistance of an object to acceleration, emerges as a property of information stability. To move an object is to disturb its informational structure, and the resistance is the network's reluctance to reconfigure. When one sees the universe this way, every event becomes a negotiation between energy and entropy, between local information and global equilibrium. The cosmic web of galaxies, the orbit of a planet, the collapse of a star, all are emergent features of a single principle: information seeking harmony. Gravity, the gentlest of the forces, becomes the universe's most eloquent form of communication. It tells us how information flows. At microscopic scales, this interplay may reveal itself in the behavior of quantum systems. Experiments now under development aim to detect whether two small masses can become entangled through their mutual gravitational influence. If successful, these experiments, led by teams such as those of Chiara Marletto and Sugato Bose, would show that gravity itself must carry quantum information. That would mean gravity is not merely compatible with quantum mechanics, it is born from it. The mathematics of this possibility is mesmerizing. In quantum theory, information does not simply move, it interferes, superposes, and entangles. If space-time geometry arises from these processes, then curvature is not static, but oscillatory. Gravity would have quantum phases and patterns, perhaps giving rise to the tiny fluctuations that seeded galaxies in the early universe. The faint ripples we detect as gravitational waves could be large-scale harmonics of an underlying quantum symphony. At the horizon of a black hole, the connection between entropy, information, and gravity becomes most intense. The black hole radiates as a perfect thermal body, its temperature inversely proportional to its mass. As it emits radiation, it loses entropy, releasing stored information back into the universe. The process is slow but inexorable, an informational evaporation. If gravity is the thermodynamic drive toward equilibrium, then the life cycle of a black hole is its ultimate expression. Formation concentrates information, radiation releases it. This leads to an even deeper question. If geometry and information are one, what is the universe ultimately doing? It may be computing itself. Every interaction, every change in curvature, every transfer of energy corresponds to an update in the cosmic database. The expansion of the universe could then be interpreted as the growth of its informational capacity, the increase in the total number of correlations that can exist. Entropy does not mark decay, but creativity, the emergence of new configurations of information. The laws of physics would, in this sense, be compression algorithms, rules that describe how information organizes itself efficiently. Einstein's field equations would be one such rule, encoding how geometry summarizes information flow with minimal redundancy. Quantum mechanics would be another, dictating how probabilities store the maximum possible knowledge under constraint. The harmony between them, the quantum origin of gravity, would be the signature of a universe that optimizes meaning. When seen in this light, gravity is not an anomaly or a leftover mystery, but the natural outcome of the universe's most fundamental tendency. Wherever information concentrates, curvature arises. Wherever it disperses, space expands. The equilibrium between these processes defines the large-scale behavior of the cosmos. Stars shine, galaxies spin, and time flows because information never stops moving toward balance. Perhaps one day, physicists will write the equations of gravity entirely in the language of quantum information, with entropy, mutual information, and entanglement replacing curvature and energy momentum. When that happens, we may discover that the field equations of space-time are no more fundamental than the equations of thermodynamics, that both are shadows of the same deeper symmetry, one that governs how information generates reality. Until then, every fall, every orbit, every gravitational wave reminds us that we live inside a universe driven not by force, but by knowledge. The sun curves space around it because its information content warps the surrounding field. The Earth moves through that curvature because, in doing so, the total entropy of the system increases. Gravity is not attraction, it is balance. It is the quiet, constant whisper of information finding its way home. For more than a century, gravity has remained the most mysterious of the fundamental phenomena, stubbornly classical in a universe otherwise ruled by quantum laws. Yet, as the 21st century unfolds, physicists are bringing gravity into the laboratory. They are devising experiments delicate enough to test whether spacetime itself carries quantum information, whether the faint pull between two particles can entangle them, and whether gravity, at its core, is an emergent property of information flow. The dream of uniting general relativity and quantum mechanics has long seemed unreachable because the scales on which they operate differ so vastly. Quantum effects dominate at the Planck length, far smaller than any current experiment can probe, while gravity reveals itself most clearly in massive systems across astronomical distances. But the revolution in quantum technology, the rise of superconducting circuits, optical traps, and ultra-cold atoms, has given physicists new tools to explore the middle ground, where the quantum and the gravitational might finally meet. One of the most ambitious approaches comes from teams led by Sugato Bose in London and Chiara Marletto and Vlatko Vedral in Oxford. They propose a simple but profound experiment. Imagine two tiny spheres, each containing billions of atoms, levitated in perfect isolation by magnetic or optical fields. If gravity can transmit quantum information, then these two spheres should be able to become entangled solely through their gravitational attraction. No other interaction would be allowed. Every electromagnetic, thermal, or mechanical influence would be screened out. If, after some time, measurements show that the spheres share quantum correlations, it would be direct evidence that gravity itself is quantum in nature. Such an experiment would be the first glimpse of quantum gravity in action, not in the curvature of distant galaxies or the depths of black holes, but in a tabletop laboratory. It would confirm that gravity is capable of mediating entanglement, implying that space-time must possess quantum degrees of freedom. The challenge, however, is immense. The gravitational force between such small masses is unimaginably weak, about 10 to the power of minus 24 newtons. Achieving the required sensitivity means isolating the system from every source of noise, from cosmic rays to vibrations caused by footsteps in the laboratory. Yet progress is steady. Advances in quantum control and cryogenic engineering are pushing the boundaries closer each year. Researchers have already demonstrated quantum interference in particles as large as molecules containing thousands of atoms. Optical tweezers can now suspend nanoscopic objects in near-perfect vacuum, maintaining coherence for seconds at a time. It is only a matter of time before these techniques converge with the precision needed to reveal gravity's quantum face. Beyond direct experiments, physicists are also using quantum computers and simulators to explore the informational structure of spacetime. By encoding simplified versions of the holographic principle into networks of qubits, they can study how geometry emerges from entanglement. In some of these simulations, information injected into one part of the system reappears elsewhere in patterns mathematically equivalent to signals traveling through a wormhole. These laboratory wormholes do not connect physical locations, but they demonstrate that the equations of gravity can arise naturally from quantum information processing. Such quantum simulations mark a new era for theoretical physics, one in which equations once confined to chalkboards become programmable systems. They allow physicists to test conjectures about holography, entropic gravity, and emergent spacetime by building miniature universes made of information. The results so far suggest that geometry, thermodynamics, and quantum computation are inseparable aspects of a single framework. Space bends, time flows, and gravity arises whenever information reorganizes itself coherently. Meanwhile, astronomers are also probing the cosmos for signs of gravity's informational nature. Precise measurements of gravitational waves, recorded by detectors like LIGO and Virgo, offer a new way to test the fine structure of spacetime. If gravity is emergent, its waves might carry subtle signatures of quantum information flow, small deviations from the classical predictions. Future observatories such as the Laser Interferometer Space Antenna will extend this reach, listening to lower frequency waves that traverse the entire universe. Each detection refines our picture of how geometry behaves under extreme conditions. On even larger scales, cosmologists examine the distribution of galaxies and the cosmic microwave background for patterns that might hint at information-based gravity. If entropic forces influence cosmic expansion, the effects could manifest as slight deviations in how matter clusters or how the universe's acceleration changes over time. The James Webb Space Telescope and other deep survey instruments may provide the data needed to distinguish between traditional dark matter and emergent gravity models. These experiments and observations are not merely about confirming theories. They are redefining what physics means. For centuries, science has described the universe in terms of matter and energy moving through space and time. But if gravity truly emerges from quantum information, then matter, energy, and even space-time are not ingredients of reality. They are byproducts of computation. The fundamental question becomes not what is the universe made of, but what is it calculating? In this new paradigm, every process is informational. The collapse of a wave function, the emission of a photon, the orbit of a planet, all are updates in the universal algorithm. The laws of physics are not prescriptions written outside the universe, but the evolving logic by which information reorganizes itself. The speed of light may represent the maximum rate at which information can propagate. The expansion of the universe may correspond to the growth of its information capacity. Even consciousness, that most elusive of phenomena, may be a self-reflective loop within the network, the universe knowing itself through information flow. Yet the beauty of this view does not diminish its rigor. Each experiment, each calculation, brings the abstract closer to the tangible. When gravity is tested in quantum laboratories, we are not merely measuring numbers, we are touching the foundation of reality. The weak pull between two suspended particles becomes a dialogue between information and geometry, the smallest whisper of the cosmos telling us how it computes its own existence. If these experiments succeed, they will mark a profound turning point. For the first time, we will have evidence that space-time is not fundamental, that the curvature of the universe emerges from the statistics of quantum information. Einstein's geometry and Planck's quanta will finally converge into a single description, not a mechanical unification, but a conceptual one. Gravity will be understood as the geometry of meaning itself, the shape taken by information as it balances and evolves. The frontier of physics is shifting from the study of forces to the study of information flow. The next generation of scientists will not look for particles, but for patterns, for the ways in which entanglement and entropy weave the fabric of reality. Their laboratories will not only measure, but simulate. Their equations will not only describe, but compute. And through their discoveries, humanity will move closer to answering the oldest question in science. Why does anything exist at all? Perhaps, in the end, existence is simply what happens when information finds a way to know itself. Gravity, the quiet architect of the cosmos, is the curvature of that knowing, the gentle geometry of understanding expanding through the universe. If everything we have discovered so far is true, then the universe is not a collection of particles moving through an independent arena of space and time. It is a single, self-referential computation, unfolding according to the laws of quantum information. Every atom, every star, every mind is a configuration of data, an intricate arrangement of correlations in a cosmic network that has no outside. Reality is not a thing, but a process. And that process is the continuous evolution of information. At first, this may sound abstract, but the idea has grown naturally from the logic of physics itself. In quantum theory, the state of a system is described not by position and momentum, but by a wave function encoding probabilities. Those probabilities are information. In thermodynamics, energy and entropy are linked by the flow of information. When a system exchanges heat, it exchanges bits. In relativity, the curvature of spacetime arises from energy and momentum, which in turn are expressions of information density. The threads connecting these disciplines converge toward a single conclusion. The universe is built not from matter, but from meaning. Every physical law we know becomes an algorithm for information processing. The Schrödinger equation governs how information evolves in time. The Einstein field equations describe how it organizes into geometry. The laws of thermodynamics ensure that information flows toward equilibrium, while quantum mechanics allows that flow to occur in superposition. Even the constants of nature, the speed of light, Planck's constant, Newton's constant of gravitation, act as conversion factors between different expressions of information. From this perspective, the universe resembles a vast quantum computer, though not one built by anyone or housed anywhere. Its qubits are the fundamental degrees of freedom of reality, perhaps tiny loops of space-time, or more abstract entities that precede geometry itself. Their entanglement encodes space, their interactions create time, and their collective behavior generates everything we experience as physical. Every process, from the fusion in stars to the thoughts in our brains, is a computation within this universal quantum engine. In this picture, space-time is not the stage, but the script. Its curvature, expansion, and topology represent the flow of information through the network. When entanglement increases, geometry connects. When entropy grows, time advances. The passage of time is simply the progression of computation. Each moment, a new line written in the code of the cosmos. What we call causality is the consistency of that code, the requirement that information never contradict itself. If reality is a computation, then the laws of physics must also define the universe's error correction protocols. Quantum mechanics ensures that information is conserved. It can change form, but never vanish. Even black holes, once thought to destroy information, now appear to preserve it holographically on their horizons. The holographic principle becomes the universe's checksum, ensuring that no bit is ever truly lost. The cosmos safeguards its own coherence. This vision also transforms our understanding of complexity and life. The emergence of organized structures, stars, galaxies, cells, minds, is not a cosmic accident, but an inevitable outcome of information seeking new modes of expression. Complexity grows where information flow becomes self-referential, where systems begin to process and react to their own data. Life is the universe folding back on itself, a localized feedback loop in the grand computation. Consciousness, in turn, is information aware of its own meaning, the algorithm glimpsing itself. From galaxies to neurons, the same mathematical patterns appear: feedback, entanglement, self-organization. These are not coincidences, but signatures of the informational substrate beneath all things. The golden spirals of galaxies, the branching of trees, the structure of neural networks, all mirror the universal tendency toward efficient information distribution. The laws that govern stars are not fundamentally different from those that govern thought. Both are expressions of the same computation, scaled and contextualized. Even the expansion of the universe takes on new significance. As space grows, it creates room for new correlations, increasing the total capacity for information storage. The accelerating expansion may be the result of the cosmos optimizing its informational architecture, stretching to accommodate the growing complexity within it. Dark energy could be the informational pressure that drives this evolution, ensuring that the universal computation never stagnates. This interpretation brings an almost poetic unity to existence. The Big Bang was not an explosion of matter into space. It was the initialization of a computation, the moment when information began to differentiate. The laws of physics were the initial conditions of the algorithm, and everything that followed, from the birth of galaxies to the emergence of thought, has been the unfolding of that code. The heat death, predicted for the distant future, may not be the end, but the final state of maximal informational balance, when every possible configuration has been computed. In this final vision, gravity finds its true meaning. It is not a separate force, but the geometry of information flow, the way the universe shapes itself to ensure that meaning spreads evenly. Matter tells spacetime how to curve because matter is concentrated information, and spacetime curves to distribute that information harmoniously. Gravity is the equilibrium between concentration and connection, the silent arithmetic that keeps the universe coherent. If one could step outside this system, if such a thing were possible, and look upon the universe from a purely informational perspective, one would see no objects, no distances, no moments. One would see patterns, correlations pulsing, entanglements forming and dissolving, networks expanding in luminous intricacy. Every galaxy would be a cluster of data nodes, every consciousness a subroutine in the cosmic computation. The entire cosmos would shimmer as a living equation, not random, not predetermined, but self-organizing, self-referential, self-aware. Perhaps the greatest implication of this view is philosophical. It suggests that meaning is not imposed upon the universe by observers. It is inherent in its structure. The universe does not merely allow consciousness, it requires it. Observation is participation, and participation is computation. Each act of knowing integrates the knower into the known, deepening the entanglement that sustains reality. To be conscious is to be part of the universe's self-description. And so, after centuries of searching for fundamental particles, we may find that there are none. There are only relationships, patterns, and probabilities. Bits of quantum information woven into the appearance of solidity by the laws of entanglement. Space, time, matter, and energy are emergent illusions, beautifully consistent projections of a deeper informational order. Reality, at its root, is meaning itself becoming aware. Gravity, that ancient mystery that guided the stars and held our feet to the ground, may be the final clue. It is not the force that binds the cosmos, but the curvature of its understanding, the shape of knowledge seeking equilibrium. In the end, the universe may not be made of particles but of purpose, not of substance but of significance, not of energy but of information, flowing endlessly toward balance. And when the last star fades, when the final computation completes, what remains will not be emptiness, but completion. The universe, at last, knowing itself perfectly.